everyone, my name is Sufyan Ben Daoud. I'm a business development manager with the High Precision Analog Group at Texas Instruments. And we're here today to talk about various trim methodologies, ultimately what it means to you, what it means to the application, how we can basically remedy some of the problems that are seen on other devices, such as zero drift, chopper stabilized amplifiers, or also auto zero amplifiers. Before we get started though, let me just say that there are various ways of trimming. There's pre-packaged trimming and then post-packaged trimming. Okay, let's talk about the advantages of some over the others. For example, pre-packaged trimming has been around for many, many years, many decades as a matter of fact. One of the advantages clearly is that it's a reliable, very reliable method because it's been around for so long. So people have acquired a certain level of experience and expertise dealing with it, and so it is, needless to say, probably the most reliable method or the most reliable methods because there's a variety of them. The disadvantage, though, is that when it comes to smaller packages, namely SC70, SAT23, micro SMD, what happens is because that small package is rubbing against the die, it can induce lots of errors that are highly undesirable, not just on the IC level, but ultimately at the system level for the end user as well. That could be a problem clearly for the application. How do we remedy that? We have come up with basically post-package trimming, okay? TI has them, our competitors have them. However, these also offer some advantages and likewise some disadvantages. One of the advantages of the post-package trim method is that it basically eradicates the fact that you have induced the errors by using a small package. You can now use a very, very small package, much like the SC70, the SAT23, or the micro SMD we mentioned earlier, and not have to deal with those errors in virtually just about any application that you can think of. Of course, one of the disadvantages would be that some of the manufacturers doing post-package trimming will specify a trim point. In other words, if you look at the initial offset voltage, it is just no longer valid over the entire common mode, but they'll give you a specific trim point, whereby if you were to get out of that trim point, in other words, if the nominal voltage is 3.3 volts, what happens if I'm at 2.7? What happens if I'm at 1.8, 4.1, 4.2? Well, then I would have to look at some quantifiable data. In other words, something like a histogram in a data sheet. So ultimately, it is you, the end user choice, to look in a data sheet and determine whether or not this is applicable and this is suitable for whatever application you may be considering this device for. An example of a post-package trim method would be something like an OPA 376 built on a pure CMOS process at 5 volts and achieving 25 microvolts of initial offset max at room temperature clearly. Again, going back to the various trim methodologies, we mentioned Zener zapping. That's probably one of the oldest one that's been around for the better part of 50 years. Laser trimming, link trimming, double EEPROM, which is usually not so much for standalone IC devices, but really on a subsystem or system on chip type of packages. And then E-trim, which the OPA 376 is built on, some of our competitive, trim methodologies, etc. So ultimately, it basically comes down to the user to look at the data sheet and determine which one is the better one for a given application. Speaking of applications, there are, of course, many of them where E-trim would make sense, and there are many of them also where a zero drift technology would make sense over an E-trimmed or a trimmed device. Here's an example. If we're talking about an industrial application like downhole drilling, for example, where temperatures are so extreme they can reach up perhaps to 200 degrees Celsius or even north of that. The problem is that when you use an E-trim device, you're not likely to get the same temperature drift or the temp code that you would normally get with a zero drift device, and hence the name zero drift, by the way. These are usually well below a microvolt, okay? Well below microvolt, meaning sometimes even below 100 nanovolts. 85 nanovolts is not that uncommon, whereas with an E-trim device, it's really upwards of 100 nanovolts, perhaps even reaching up to 500 nanovolts. So you see the difference there. I'm saying this because, again, if you reach up to extreme temperatures, consider using a zero drift instead of an eTRIM device. If you're not, in other words, a medical instrumentation is a perfect example where the temperatures are not as extreme. Perhaps, you know, an apparatus sitting in a lab, perhaps a lab chromatography type application, a pulse oximeter, where it's basically sitting in the lab in an environment where temperatures don't exceed 70 degrees. You probably should consider an eTRIMmed or a trimmed device, perhaps a post-package trimmed device versus a zero drift, because of, number one, the cost savings, number two, the miniature packages, and number three, not having to deal with the chop-in frequencies or the higher input bias current induced by the charge injection of a zero drift, a chopper, or an auto zero type of amplifier. Thank you for watching. For more information, please go to the following web addresses.